Hi, this is the second of 3 lectures on refraction. This video will focus on lenses. All right, so when we talked about reflection, we talked about the different types of mirrors. And we learned that there were converging and diverging mirrors. Lenses also can be shaped. They can be very thick and have thick centers, converging lenses, or they can diverge light by having a very thin middle. The name of a converging lens is a convex lens. The name of a diverging lens is a concave lens. You may notice that this is opposite. Mirrors that are convex diverge light, and mirrors that are concave converge light. So think of it this way. In terms of what diverges and converges light, lenses and mirrors operate on opposite principles. Mirrors reflect light, but lenses refract light and light goes through them. So the name of the shape of the lens that converges light is going to be opposite to the name of the shape of the mirror that converges light. Converging mirrors and lenses both converge light onto a focal point. For lenses, a convex lens, when light enters the lens, is going to be refracted towards the normal. And because it's rounded, when it comes out, it's going to come out at a different angle than it went into. And it's going to be refracted down and converge onto a common point. Converging lenses and mirrors always have a positive focal point. So that's something they have in common, even though their shapes are opposite. A concave lens diverges light. So when light goes into it, it refracts upward because of the shape of the surface that it's on, and then it refracts even more outward. So the effect is that it refracts the light such that it's diverging from a common focal point. Concave lenses diverge light, just like convex mirrors diverge light. They always have a negative focal length because they diverge light. Once again, we're going to draw ray diagrams to show the type of images that form. And we'll have P for the parallel ray. We'll have F for the ray that's drawn towards the focal point or away from the focal point. And then we'll have the M ray, in this case, that goes straight through the middle of the lens. The other thing I want to mention to you is that you can have 2 different types of images. You can have a real image that can be projected where light intersects. So in certain cases, a converging lens, convex lens, if the object is far away from the focal point, just like the same conditions for a converging mirror, if the object is far away from the focal point, then a real image will form and it will be upside down. The real image is going to have a positive image distance, and it's going to have a negative height or negative magnification. It is going to, instead of with mirrors, our real images formed where the light rays were, where the reflected rays were, which was on the same side as the object. But for lenses, because the light is going through the lens, a real image is going to form on the opposite side of the lens than the object. But we're still going to say that it's a positive image distance. If something diverges light, right, like the that when I draw my three rays, right, the P ray gets diverged away from the focal point on the same side as the object. The F ray just goes through the center of the lens. The center goes straight from the top of the object to the focal point. And notice that these two, well, actually it goes towards the focal point, but then it bounces parallel. Notice that this ray and this ray are going to never meet, ever, 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 ever. So no real image can ever, ever form here. So if you look on the other side, the constructed rays, two of them will meet. So you'll get an image that forms that's upright, but it's not something that's where, this dotted ray is not a real ray of light. The red ray is, but it's not a real ray of light. So the point is that you're going to get a virtual image forming. But notice, with mirrors, the virtual image formed behind the mirror where there was no light. But for lenses, it forms on the other side of the mirror, on the same side as the object. Now, a convex lens can make a virtual object too, under the same conditions that a converging mirror can, where the object is in between the focal point and the lens. So if I have an object here, I'm going to form an image over here, and that'll be virtual. So here's a diagram of that, right? If I have an object here, so I draw parallel and then down to the focal point. And then we only really need two rays to be drawn. So I'll just draw this ray that goes right through the center from the top. These will never meet, right? But if I dot them back, you will get a virtual image. Now, one thing to notice is that the virtual image is the magnified image that a magnifying glass makes. It makes a virtual image. You cannot project it. So we can derive the same lens equations, and we'll still use the same rule that DI is going to be negative if it's a virtual image. If it's a virtual image, the only difference will be that the object and the image are on the same side of the lens. If it's a real image, it's going to be upside down, just like it was for mirrors. It's going to be on the other side of the lens, behind the lens. And F is going to be negative as a diverging lens, and F is positive for a converging lens. Our equations are going to be the same. 1 over di plus 1 over dou equals 1 over F. And the magnification is di over dou, negative di over dou. So just to remember, to kind of sum it up, this is a chart, just like the chart that you had for mirrors. If it's a concave mirror, it's diverging light. So no matter where the object is, it is a negative focal point, and it will end up having a negative image distance because it's virtual. It's forming on the same side as the object, and virtual images are always upright. The convex lens, which converges light, has a positive focal length, and it will have two different images form. If the object distance is greater than F, it'll make a real inverted side on the other side. But if the object distance is less than F, it'll be virtual and on the same side and upright. So this looks very similar to the mirrors, but it's a good thing to go by, and I would definitely copy it down for both mirrors and lenses. So here's an example. Magnifying glass is used to view a stamp that is 5 centimeters from it. So a magnifying glass is thicker in the middle. It's a convex lens. So you know already that this is a converging lens. So F is going to be positive. Its focal length, therefore, is positive 20 centimeters. Its image distance, that should be, sorry, that's a typo. That should be dou, and this should be dou. This should be di, that's right. This should be dou. The object distance is 5 centimeters. Notice that this is less than F, so we should expect a virtual image, and it will be upright and magnified. So when we do the math, 1 over 20 equals 1 over 5 minus 1 over di, and we get negative 0.15 centimeters, and di equals negative 6.67 centimeters. The image is virtual, upright, and 6.67 centimeters on the same side of the lens as a standard. And that would be the magnified image that you would see if you used a magnifying glass. So make sure that you have the sign conventions under control for lenses. Remember, really they're the same, except that the name of the lens is opposite to the name of the mirror. And that the virtual images don't form on the opposite side. They form on the same side of a lens as the object.